And I just want to say one thing to the students. What I would like for you students to know is that we will be taking questions to the speaker at the end. Of course, you can put those questions in the chat and we will try to go through those if you have questions about what the speaker has to say today. Otherwise, I'm going to hand this off to Professor O'Brien to introduce our distinguished lecturer for today.
Well, I've been instructed to reduce it down to 10 seconds, but I have maybe just about twice that amount or 3 times that amount to introduce Matt. I have to say it's truly an honor to have Professor Matt O'Donnell as an Illinois ECE Distinguished Colloquium Speaker today. This talk is also under the auspices of the Distinguished Lecture Program of the IEEE Ultrasonics, Electrics, and Frequency Control Society. I've been acquainted with Matt professionally and personally for about 4 decades. He is a well-recognized pioneer and scholar at the national and international levels and has had many significant contributions to advance biomedical engineering. This colloquium speaker announcement the announcement recounts his academic and industrial positions, as well as many well-deserved honors and awards. I'll let you read those from the announcement. I'm not going to repeat them. Instead, I encourage you to read and aspire to them. What Matt has and continues to emerge, what Matt has done and continues to emerge from is his creativity, his productivity, and his fundamental observations that have changed the landscape of diagnostic ultrasound. By any measure, I think you would recognize if you start reading his early work, middle work, current work, you'll realize he is a world-class leader, a pioneer, a scholar, and a well-recognized educator also, as you're going to learn from this talk today. So Matt, I would like to turn it over to you and welcome.
Okay, so I thank you very much. Thank you for inviting me to come to Illinois. Lunch today was great with you guys. I enjoyed it very much. And hopefully dinner tonight will be even better. So, start please. Okay, oh, I'm sorry. I have to change the camera. Should have done that before I start. So, everybody gets in real time to see what your Zoom skills are. There we go. Okay. Sorry, I should have a joke while I'm doing that, but I don't. Okay, so you should see me looking at you and the slides. Everything okay?
Yep.
All right, and also please anybody mute your audio out there, because I know I always forget to mute my audio when I'm listening to somebody. So just ask you to do that. So I'm going to do a quick spin about where sonics, ultrasonics, and photonics come together. This is an area which I've been interested in for over 25 years. And it started as a little hobby, and now it consumes almost all of our lab is looking for different applications of bringing these 2 technologies together. There are 3 areas which I'll show you just as examples of how you can leverage these 2 tools to do some really interesting stuff in biomedical engineering. So the first will be on photoacoustic imaging, which we have here, and that's where light generates sound. The second will be laser ultrasound, and also some photoacoustics involved in that too. But this is laser ultrasound where light detects sound. So that's the essential technology there. And the third is in the area where sound tickles light. And so this will give you an example from that, which is optical coherence elastography, where sound modulates light. So let's get into the first one, photoacoustic imaging. Photoacoustic effect. Discovered by Alexander Graham Bell. Yes, the guy who invented the telephone. It was called the photophone when he first found this. And it's a fairly simple effect, but has major consequences. So consider this little simple Gedanken experiment. Look at, you have a piece of something mimicking a piece of tissue, and inside of it, you're going to have an optical absorber. But we're going to have an ultrasound array that's going to detect the results of an interaction. The interaction is we're going to bring in light. But unlike traditional optical imaging, where you spatially confine the light, but have a CW illumination, so it's temporally broad, but spatially compact, we do the inverse. We bring in light, which is spatially broad, and in fact, the diffusion of light in tissue is to our benefit because we want light to go everywhere, but it is temporally compact. And the reason for that is that when this light propagates through the medium, anywhere that there are absorbers, you'll create a little heat pulse. And that heat pulse, through thermal expansion, creates a particle velocity, which is a pressure wave. And that pressure wave can be detected by the ultrasound transducer and is given by a wave equation. I think this is the only equation today. But anyway, is that the left side is a wave equation for the pressure, and the right side is the source or drive term. But that's given by this little heat pulse. And that heat pulse, though, for the light that's going in is determined by the product of the local optical absorption of the region times the amount of light, the fluence that gets there. So what does that enable? What that allows you to do is to make a picture where the information, where the imaging information comes acoustically, but the contrast is optical, okay? So the source of the contrast in the image, the strength of an acoustic pulse like you get, like you have right there, is just proportional to how much is absorbed, okay? Now, from an optical point of view, this is great because it gets over the diffusion limit. You can go centimeters into tissue because you don't have to maintain optical coherence. All you're caring about is light, is the absorption. And as long as the pulse length is long compared to any diffusion spread that you will get as a result of diffusion, then you'll have this compact acoustic pulse coming out, which is easily realized. So it's a nice way to get around the diffusion limit. But I'm an ultrasound guy, as Bill said, and so we looked at this photoacoustics effect as a way to bridge the worlds of optical and ultrasound imaging. And in fact, there's a sweet spot, we think, in this region where you have several centimeters of penetration depth. So typically, areas where you would use 10, 15 megahertz ultrasound instead of 2 or 3 megahertz ultrasound. But you have this region where you can combine ultrasound with this photoacoustic imaging. So an immediate question is why? Why would you want to do that? Okay, this is integrated. We call it PAUS, photoacoustic ultrasound. The reason you can do that is you can bring the beautiful molecular contrast that has been developed for nearly 100 years in optics into simple ultrasound. And so contrast agents, which in traditional optics are things like fluorophores, we now make contrast agents which are absorbers, specific absorbers. And this is just a potpourri of different particles developed in our lab, other competitors' lab around the world. And this is the excitement about the photoacoustics as an add-on to ultrasound, is bringing a true molecular dimension to a fairly simple technology, ultrasound. This is just an example. It's one of the particles we have developed in our lab. This is done, obviously we're scanning out a W because we're from Washington, but the idea here is this agent is actually a combined ultrasound and photoacoustic agent. Doesn't matter. What the point is that with simple ultrasound, you can bring now a molecular dimension through this photoacoustic effect. So it's exciting to be able to do that. However, for this to be truly clinically viable, you have to bring it into the clinic in the same way that you deliver ultrasound to clinic. So that means, first of all, you require real-time frame rates for these interleaved images. You can't give up anything in ultrasound to add this molecular dimension. The second is that cost effectiveness, size, portability are very, very important for ultrasound. But in the early days of photoacoustics, they were not. So the image I just showed you on the previous slide, that was the laser that was used. That's a unit Sharpie right there. So you can see that's the pump laser, the OPO, the power supply, and there's a cooling system underneath, which is cooling this guy. Now, certainly you can make it more compact than this, but nowhere near the level that you have here, which is where ultrasound handheld systems will go. So this is a major limitation. And the last is that having lasers come in different directions into the body is fine, but the way in which we do ultrasound is through handheld probes. And so doing things in real time with handheld probes so that the user can be seeing the images to guide procedures or to do instantaneous diagnosis is, if you're going to add this optical dimension, then it has to be seamlessly integrated with the probe. So this is something which been a system working on for about a decade now, which was to change the way in which photoacoustics is performed. And that is, the traditional systems to date have been to use an ultrasound array, but then integrate a big laser which pumps out a single optical pulse into the tissue. We substituted an approach which is a la kind of ultrasound, which is we're going to scan fast, very, very fast. We use low light levels, but scan very, very fast, and it put a challenge into the optical delivery system. But what it does is it dramatically reduces the burden on the laser. So if you look at that laser that I showed you that we used for those original images, our first step in this evolution was to replace it with this laser. And there's your unit Sharpie here. So this is something you can hold in your hand. So there's a laser you can just hold in your hand. It functions at a single wavelength, 1053. It's a kilohertz pulse repetition rate and about 2.2 millijoules, about 100 times lower pulse power than this guy. But again, it's this delivery system and fast scanning that we have to design to take advantage of this technology to produce photoacoustic images of the same quality. Well, just to show you, I mean, I'm not going to go through all the details how we put that together, but you can do it with that kind of technology. This is just a simple experiment that we did, which mimicked drug delivery, guidance of drug delivery, as is done traditionally with ultrasound, where you bring a needle into, and this is just a excised tissue sample, not in vivo, but you bring it in, you then deliver an agent, but the agent in ultrasound you can't see. In photoacoustics, you can see it. Why? Because you can label it molecularly. Okay? So these are these pauses images. So we're interleaving these fast photoacoustic images with ultrasound images in real time, where the photoacoustics brings us molecular information and the ultrasound brings us anatomical and sometimes functional information. Okay, now in the last few years, we've evolved that system one extra step, and that is to try to do spectroscopy. This big laser, the reason why we use it, and most labs use some equivalent of this, is because we can scan wavelengths and get optical spectrum through photoacoustic measurements. We leverage this technology that we have here, this diopole solid state laser, into a tunable Ti-sapphire laser that's able to sweep over near IR range, which is appropriate for biomedical applications, but again, at these high rep rates, but slightly lower, about half the energy that we had for the single wavelength, but still a very efficient approach, and again, in this fast scanning motif. So this is a system we put together. It's a real-time approach, and I'll just show you some images, but before I do that, I wanted to mention two effects quickly, which have limited spectroscopic measurements in vivo. And the two major limitations that, for spectroscopic measurements in vivo are, number one, tissue motion. The reason being that you must sweep through a range of wavelengths. Each wavelength takes a laser pulse. So to get a spectrum at a pixel level, to get a spectrum, you must go through multiple wavelengths. And so with the slower lasers that have been used to date, that could take seconds to sweep through there. And so just by movement of your tissue, you can warp or color spectra, which have nothing to do with molecular properties or just due to motion. A second effect which can color a spectra is fluence. If you remember what I said from the photoacoustic equations, is that heat generated is proportional to the absorption and the fluence. And you really want the absorption because that's the fundamental molecular characteristics. However, the fluence in tissue, because of this diffusion effect, the fluence can vary as a function of wavelength. So depending where you are, and make photoacoustic measurements, again, you can color that spectrum because of the fluence variations with wavelengths, which has nothing to do with the molecular characteristics of the object in which you're trying to image. So those two big effects, this integrated photoacoustic ultrasound with spectroscopy, spectroscopic laser, by doing it fast and integrating this delivery system into it, we're able to, I'm not going to say solve yet, we're able to address at this stage, we're almost solving, I'd say, we're able to address these two challenges of tissue motion and fluence variation. So what we can do is, because we get these images still relatively fast, but still subject to motion, we have interleaved high frame rate ultrasound pictures, which we just use traditional motion tracking, speckle tracking for your ultrasound folks, to re-register the photoacoustic images. And so we can eliminate the motion artifact. More importantly, though, for any system, no matter how fast it goes, is that the fluence, we can address the fluence variations through this fast scan approach, because we can illuminate the object from different spatial positions. By having this heterogeneity in spatial positions, we can map the photoacoustic signal changes with position, and from that, of the same object, okay, so of a common object that you map those variations can only be due to fluence variations because it's the same object, so you can compensate for them and eliminate the fluence variations. So that's the approach. Not only does this fast scanning allow us to integrate real-time photoacoustic and ultrasound, but allows us to address two of the major limitations to date in doing in vivo spectroscopic imaging with photoacoustics. Okay, so let's just show you sort of in simple fashion how this works. So this is exactly the same experiment I showed you before, but now I'm injecting an agent and with the needle and all that, except when I scan through, I went through. Oh, you guys saw it here. So I was sweeping wavelengths, right? So it came along, went boom, 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 boom. And what I was doing is sweeping wavelengths as I was going through that scan. So now I have images of my object, but at different wavelengths, right? So if I can correct for the fluence and correct for the motion, then I can look at the spectra at a pixel level. Now, this was a stationary target, so all we did was fluence compensation. But when we do that, we can look at pixels and say these pixels here, here, and here have very similar spectra. What are they? Those spectra are matching to the contrast agent. However, when I look in other pixels, here, for example, which are those associated with the needle, we get a fundamentally different spectra. Why? Well, of course, the needle has different absorbers than does our contrast agent. So here now is we can do a very simple trick, which is used in all sort of systems people in ECE do this stuff all the time. You can do projections, right? So you can decompose these signals, do projections, and so you can make images of the components. And so that's what we do. So we have just our raw photoacoustics, but this is the power of the spectroscopy. The spectroscopy now allows us to separate the components. So here, and this is sort of a validation, before we inject any of our agents, we see nothing here and we only see the needle. Then we start to inject while the needle's still there. We see both, we pull out the needle, and of course, all we see left is the agent, okay? So you can do that. This is just a simple demonstration, but you can do that for a multiplicity of agents, because if you have a unique optical spectrum and you correct for fluence and motion, then you can capture that. This is an in vivo test in a small animal, just showing you can see the motion. Here's that scanning through wavelengths like we did. And so now you get these images at different wavelengths. If you don't do any motion correction, you get this blurry image and you can't match spectra well. When you correct for motion, you can match spectra in vivo almost perfectly to the contrast agent spectrum. And you can get very robust images showing exactly concentrations of where that agent is. And we actually did a really crummy job of delivery here, because we're supposed to try to get a region in here, but it was validated afterwards and at least proved the technology of being able to do this in real time. So as a quick flash, through photoacoustics, but this is a piece about where you can use light to generate sound. And the primary motivation for that in biomedicine is for going that molecular, bringing a molecular characteristic to the simple imaging modality of ultrasound. Okay, let's go to the second one. Laser ultrasound, where light detects sound. Okay, so let's do the same experiment we just did before, which was a photoacoustics. So we're going to bring in a pulsed laser radiation, but this time we're going to tune the wavelength to the material we're interested in such that all of that energy is absorbed within a few microns of the surface. So we get a very, very efficient transfer of optical energy into acoustic energy that launches an acoustic wave into the material. And then we're going to reflections, so traditional ultrasound reflections that come back, we're going to detect optically. Now, why would you want to do this, both optical generation and detection? It's so that you have no contact. So there's absolutely no contact whatsoever with the material. This is important for a number of different applications, as I'll get into in just a minute. Okay, now, laser ultrasound's been around for 30-something years, but its Achilles heel has been the detection sensitivity on the optical side. It's typically 3 orders or so magnitude worse detection than your best piezoelectric transducers. What we've developed over a period of about a decade now is some tricks where we've done 2 things. I'm not going to go through this whole interferometer, but we did 2 things to overcome that, that limitation of traditional optical detection. Number one is we changed the interferometer type to one that's called a Sagnac, which gets rid of a reference arm. So the reference arm of a traditional optical interferometer we replace with something which is a time delay. That is, you have both a true pulse or a sensing pulse and a reference pulse are just time delayed and reflect off the same surface. So the same surface acts as both source and reference, okay? Which improves efficiency greatly when you have rough surfaces, non-metallic types of surfaces. That's one trick. The second trick is we use integrated optics. I know you guys at Illinois are big leaders in these types of technologies, but we use integrated optics and polarization maintaining devices and a differential approach. And again, afterwards, anybody wants me to talk through this, I love to talk through the details of this guy. But it's overcome about 2.5 orders of magnitude of the sensitivity limits, which means that now we have something that actually functions like a pulse echo ultrasound transducer, but is entirely non-contact for application. So here is one application, which is actually the original motivation for the work. This is while I was still dean and was giving an alumni tour through Boeing. And they have this problem that the composite materials, which are going into the modern aircrafts, like the 787 especially, are dramatically changing aerospace, but they have a problem. The problem is they really don't know very well how they damage. So you just saw this. Yes, you did see that. That truck just ran right into the fuselage of that plane. I'll let it play again. Bam! Okay? You say, oh, that's so funny. This happens once per year on average with a worldwide fleet. Okay? Now, it may not be a truck. It may be a lightning strike. It may be something else. But there is one major collision on average once for every aircraft in the worldwide fleet. It's not what clear to do. Okay, that truck guy hit there. What do you do? If it was a metal aircraft, you go up and look, because there's a very strong correlation between the visual damage and the damage inside. That's not true for composites. And so what Boeing, and when I took this alumni group through, I said, oh, opportunity, right? So is there a way for doing non-contact, fast ultrasound inspection in sight to look at damage in composites? So that's what we did. So we used this system, built this system for that. So just for the non-ultrasound people, quickly, the type of images I'm going to show are a little unusual. But A-scan is just a single one line, just like in radar or ultrasound, one line, which is range at one position. You then scan that position to get B-scans, so you get cross-sectional images. But what I'm going to show you are C-scans, which are you get a volumetric data but I'm going to present the images back to you slice by slice by slice, and you'll see a movie where you'll be looking from the front surface of this part to the bottom surface of the part. Okay, and this is just an example. So here is an impact damage on a composite sample. Visual inspection is this little dot right here in the middle. And we compared our little scanner, which took a few minutes to do the scan, versus 3 hours and many thousands of dollars on a micro CT system in UW Hospital. That was interesting to write on a grant for this. And we're going to do a comparison. So I'll play the movie, but remember the movie is we're scanning from top to bottom of this sample. And so what you're seeing is the flaw, the damage. And these are the propeller delaminations, which are known, and you can see here almost identical information you're getting from the laser ultrasound and the CT. Huge volume involved in that damage, even though surface inspection is like the size of a small marble or ball bearing. Okay, so looks pretty cool. But I'm a bio guy, right? I'm a bioengineer. So that was cool. That was fun, you know, and you got to get alumni happy and stuff like that. But it was, okay, how do we actually use this stuff? And so in the last few years, we've been looking at ways to use this non-contact detection for biomedicine. And so 3 we've pursued. One is label-free flow cytometry, that is not using any fluorophores to do cell separations in flow cytometry. The second is to try to do point of care histology using non-contact photoacoustics. And the third, which I will show you a few slides of because I think it's interesting. I mean, I think it's a potentially real application, which is scatter-free spectrophotometry. Okay, so what the hell does scatter-free spectrophotometry mean? Well, first of all, let's talk about what a spectrophotometer is. Many people use these, especially in the biomedical sciences and the chemical sciences. But the idea is pretty simple. As I said, optics goes into this molecular characteristics of materials. So a spectrophotometer is normally used. Let's say this is a Gedanken thing again. I have my latest nanoparticle, okay, in there, and I want to know what's the absorption spectrum of that nanoparticle. Well, I put a solution of that nanoparticle in a spectrophotometer, which just has a source and detector, and just measures the attenuation of light along a fixed light path, and from that, draws out what the spectrum is, what the absorption spectrum is, which is related to the molecular characteristics of this of the absorber or the nanoparticle in this case. What happens though if you want to look for those absorbers inside of something complex? So for example, inside of live cells. So that, by the way, is our ultimate goal, doing spectrophotometry inside of live cells. So when you do that, put these nanoparticles, well, yes, there's absorption, but there's a hell of a lot of light scattering that goes on here. And so you can't, so you have a lot of attenuation, which may not be related to the absorption and the molecular characteristics themselves. Now, there are pure optical tricks with integrating spheres and other things, but they're very sample dependent and hard to calibrate. We were looking at a very, very simple approach and a very simple system to be able to get optical spectra inside of living cells, analogous to the way you make spectrophotometer measurements in solutions. Okay, so here's the idea. The idea is we're going to make a photoacoustic system, very similar to what I talked about in the first bullet of this talk, but we're going to use the non-contact detector, which I'm talking about now in the second bullet of this talk. And we're going to, unlike what we did before, where we spread the light going in for photoacoustics, we're now going to focus the light. And so what we have is a little microscope. But we have a photoacoustic microscope, but it's 100% non-contact. And the idea is we're going to scan this to look at cells in cell culture. All right, and so a little proof of principle just of this idea is we first take and do scanning in a sample which consists of free nanorods and free cells. Our pure spectrophotometry measurements, as we said, are complicated because you have a signal that you get just from the cells themselves due to scattering and the like. But this simple system, superposition is not too bad. so when you look at the just the difference between these two spectra, it's pretty close to what the true absorption spectrum is of the nanoparticles that you're interested in, because the cells don't, at these wavelengths, don't absorb very much. Scatter a lot, but don't absorb very much. So it's not bad. However, what happens when those nanoparticles are endocytosed into the cells? So they're intimately linked, the nanoparticles in the cells, and so you can't separate in this simple way. You get these UV vis spectra. If you subtracted them, you get nonsense. You have nothing that has to do with the spectrum. However, when you do it photoacoustically, and they're outside the cells, you get this one. When they're inside the cells, you get this red one, which is very interesting. Let's look at that in the next slide. When you so the spectrophotometry measurements are garbage. They don't mean anything in this complex environment. We know that. When they're outside the cells, you get this nice simple spectrum. When they're inside the cells, you get this split spectrum. What is that? Endosomal capture. So we were able to image endosomal capture of these nanoparticles because of the blue and red shift that you have, because of the alignment. We have a particular type of nanosystem where the alignment changes plasmonic coupling, and so can change the resonance. And so we could see that. And so that's, again, our goal, is to be able to make these types of images in live cells to see dynamic processes while using non-contact spectrophotometry, or non-contact photoacoustics as spectrophotometry. Okay, flash and dash. So let's go to the third one. And the third one is where sound modulates light, where sound tickles light, okay? And the technology is optical coherence elastography. And let me give you a little bit of motivation, because we're all well, I'm a bioengineer, Bill's a bioengineer, Michael's a bioengineer, so we've got a few bioengineers here. But always we start with what's our clinical motivation, what's our biomedical motivation. And the motivation for this technology is to assess the mechanical properties of tissue types of these are small, big tissues without any contact, okay? Say, well, where would you do that? Well, one is the cornea, and I'm going to do a lot of stuff with the cornea, so I'll focus on that. But there's other places like the skin, and this is especially true for burns, and for any kind of grafting procedures is you don't want to touch, especially post-graft, you don't want to touch. And the third is very, very delicate, small samples. I'll show you work today from cornea, a little bit of skin, and I will have nothing to show here, but our ultimate goal there is to be able to monitor sort of longitudinally development of tissue types in organ on a chip type of constructs. Okay, so let's go to the cornea. And why do you want to know the elastic properties of the cornea? Well, form follows function. And the function of the cornea, of course, is the primary focusing lens of your eye. And its shape, right? Its shape determines its focal characteristics, and the shape is determined by the intraocular pressure, that is the fluid pressure that you have inside your eye trying to push the cornea out, and with the response coming from the elasticity of the cornea, all right? So the deformation, so the focal characteristics are determined by this fundamentally biomechanical effects. The clinical standard of care is they measure shape in IOP. And IOP is done either with this contact approach. I like to watch that play a while to see how many people start to have their sphincters tighten and worry about this contact in the eye. You can either get that or an air puff. I usually get the contact one, but I'm pre-anesthetized when they do that. That's how you measure IOP. And then, of course, optical imaging to look at shape. So our goals was to get much more, developed measurements for both diagnostics and guiding therapies. And so our goal is to quantitatively map elastic modulus, because all IOP measurements now assume a uniform elastic modulus for all humans. All humans have the same elastic modulus. Probably not true. So anyway, we want to do that. We try to measure IOP independent of the corneal elasticity, this technology. And finally, is our ultimate goal is to guide and optimize therapeutic interventions, because we, as I'll show you, we can do this imaging in real time. So the idea is to try to guide corneal transplant surgeries, LASIK surgeries, all these types of things with this technology. But today, I'm only, because I only have about 10, 12 minutes left, I'm only going to talk about quantitatively mapping elastic modulus with this technology. Okay, so to map elastic, so this is elastography. This is something which is has boomed in ultrasound, in magnetic resonance, and now starting to come into to optics. And the idea is to do this kind of mechanical mapping, you need three components. One, you've got to be able to image. The second is you got to be able to deform. And the third is from that, you need to quantitate to work backwards to solve inverse problems in order to get the elastic modulus. So you need non-contact imaging, quantitative approach. And for this application, non-contact deformations, because it has to be totally non-contact system. Well, the non-contact imaging was great. We just went down the hall to our friend Ricky Wong, who's one of the leading experts in phase-sensitive optical coherence tomography, and fast scanning systems. And here we can measure displacements down to the nanometer scale with these optical techniques, again in real time. And so we're leveraging that technology. And at the end, when I show pictures of people, I'll show you Ricky's group, because they've been a fun, very fun group to work with as they have this technology that we're using. Okay, the second is quantitation. And this is the concept of dynamic elastography, which is now, wow, 25 years or more old, where you use imaging systems to track the propagation of shear waves in tissue, okay? Because in simple bulk isotropic media, that shear wave speed is directly related to the shear modulus in this simple way, and the Young's modulus, which determines tissue deformations in an isotropic material, nearly incompressible material like tissue, say liver, is just 3 times that value. So from these wave speed measurements, you can directly get elastic moduli, which are going to tell you how things are going to deform, which is, of course, what you want to know for the cornea, because it's this mechanical organ. Okay, but the rub, so that's, you know, exciting, cool, let's charge. But the rub is we can't touch anything. So how do we make a deformation if we can't touch anything? So it's got to be totally non-contact system is required. Okay, so we looked at a bunch of things. The air puff, which is used clinically. Yeah, it's non-contact, but oh boy, I don't like, I mean, it makes pretty serious deformations. Anybody had, well, I can see Bill and Michael, but anybody had an air puff IOP measurement? Okay, not the nicest thing in the world, is it? So in there. So anyway, but also from a technical point of view, even though it's non-contact, it's very low frequencies. You can't get very high spatial resolution with them. It's very hard to direct them and do that. So we went back to one of our bag of tools and said, oh, let's do photoacoustics. We'll whap it with a photoacoustic thing like a laser ultrasound system, and we time and space modulate it so it's appropriately right to launch away. And we did that with pulse UV light, because UV does not propagate into the cornea very far. Problem was, to get sizable waves, we were near cooking the cornea. So that was not going to work. So we kept on coming back to, you know, but ultrasound's been doing this for 20-something years. You just get ultrasound in there. But you need ultrasound to be coupled into the tissue to do this. So one bright postdoc at a group meeting one time just said, why don't we just put it through the air? And of course, after everybody stopped laughing and started talking, and we realized, well, why not? Because actually, propagating ultrasound through air gives you almost a perfect force transducer, because that ultrasound is perfectly reflected because of the huge mechanical impedance mismatch between tissue and air. And that gives you a very large radiation force. The question is, how do you get ultrasound in air to the surface and shape it in time and space in a way which can launch the appropriate sized mechanical waves? Well, we did it. We designed a set of air-coupled ultrasound transducers. You can see this is one of the postdoc. Actually, the postdoc who had the crazy idea, we made him build the transducer too. It's just pushing around some salt on a table, just showing that this is pretty powerful stuff if you can get it through air-coupled. Well, when you go through the numbers, it turns out about 1 to 2 megahertz ultrasound will propagate anywhere from 5 to 15 millimeters in air, which is piece of cake for ophthalmology. You can just keep it about a centimeter off the surface is no problem. And you can get more than enough sound to that surface to propagate micron scale mechanical waves, which are easily tracked with OCE. So that's what we did. So we called this thing acoustic micro tapping. And so it takes air coupled ultrasound, and then we image in real time with a 4D OCT system. That is, it's 3 spatial dimensions in real time. And you do experiments like this. So you hit at the surface, and if you have a bulk material, you will create 2 waves, a surface wave or a Rayleigh wave propagating along the surface, and a bulk shear wave coming off at a fixed angle, which is constant for all tissue because it's nearly incompressible. And so you can track these things because the speed of these things, like we said, is directly related to the elastic modulus. And so there's a little bit of a fudge factor if you use the Rayleigh wave versus the bulk wave, but there's just a simple proportionality between those, okay? So how do you make wave speed estimates? Well, for example, if you just looked along one surface, say the top surface, you can make plots of xt, and just the instantaneous slope tells you what the speed is, right? Pretty straightforward. So we built it. You stick it together. We took one of Ricky's systems, one of our air-coupled transducer systems. We stuck them together, integrated them together, make it sound easy. Of course, it was a PhD student and a postdoc, about 6 months of their lives to do it. But once it's all together, you can make pictures like this. So this is, and I'm showing them at non-real-time speeds. It took 1/3 of a second to gather all of the information that's shown in these movies. What you're looking at is the grayscale now is not ultrasound. The grayscale is OCT, and it's showing the cornea, which anatomically is not very interesting other than just looking at the apex where you get a specular reflection echo. You ultrasound guys, that's a specular reflection artifact that you get, but it's optically. But what the OCE is, you're mapping, you're looking at, let me go back, I have the movies plug in, is what you're looking at is the propagation of these mechanical waves. And we're looking at the difference, but this is an animal model between 10 millimeters of mercury and 40 millimeters of mercury. And of course, it goes much faster, right? Oh, but I thought all humans were one elastic modulus. Even just IOP is part of the equation. So you can map them, you can make pictures of them. It's all wonderful, right? You do it in skin. We can see stuff in skin. Here's just simple stuff. We're looking at burn patients now. We're starting to build a robotic system to do this for skin imaging, 3D OCT and OCE combined together. Now, but wait a minute. Give me a break. Is it really this easy? No, as you might expect, right? I mean, I tried to make it like it was easy just so I could have that loaded question. So in the last about 5 minutes or so, there's more complications there. Every time it's like the classic onion problem. We just keep, peeling a layer of the onion, and there's another layer of complications. And so I'm a native New Yorker, if you couldn't tell by now. And so complications to me, that's problems. Problems I have to solve. Well, there's lots. But I'll just give you 2 what you think are the biggest ones and show you this is one of the few times in my career where a problem/bug turned into a feature. Okay, so I'll show you that. Okay, so the first is bounded waves. Okay, so the cornea is very thin. It's about 0.5 millimeter in humans, almost 1 millimeter in pigs, but still very, very thin. And our acoustic wavelengths are on the scale. They're anywhere from a few hundred microns to a millimeter. So we're right in a true guided wave situation. All right, so when we had that simple case again, where it's a bulk material and we can do instantaneous derivatives to see what the velocities and therefore what the moduli are, when you do this bounded, oh my goodness, that is a very complicated wavefront. And if you just look at the top surface, you get something like this, okay? And it doesn't make sense. You can't do simple derivatives. And in fact, people who have tried to do this get artifactual images because you just, from the cuts and bumps that are in these interference patterns, are they infer it's, modulus changes, has nothing to do with that. It's a guided wave behavior. Okay, but as good EEs and physicists is we know how to handle complicated superimposed waves. It's we look for modes and mode structures. And we did that in our case by looking at 2-dimensional Fourier transforms. And from that, we can see distinct modes, which you would expect, which are Lamb wave modes for acoustics people. our classic Lamb wave modes, and we can do theoretical calculations and match up with measurements. And so by doing dispersion analysis, we can get back to some quantitation, okay? So that's the first piece. So it's complications, but it's now you have to make sure that you have sufficient bandwidth in your system to do robust dispersion analysis. So that was the first complication which we've had to address. Okay. The second one has to do with isotropy. So when you're looking at elastography in the liver, isotropy is a very good approximation. When you're looking at elastography in the cornea, isotropy, as I'll show you, is not a good approximation. So in tissue types, there's two basic forms of mechanical testing that's done on tissue. One's a tensile test, as is shown here, and that's directly related to calculations of the Young's modulus, okay? And those types of measurements made in excised animal and even human cornea tell you that the Young's modulus of cornea is in the megapascal range. The second type of test is rheometry, or shearing tests you can make, okay? And that's just shown here. You can see the little movie, how you can shear the things. And this is a measure of the direct measure of the shear modulus, okay? But in the cornea, when people make these rheometry measurements, which we have done too, they're a little messy, but you can do them. You see you're in the tens of kilopascal range for the shear modulus. So is the cornea isotropic? Well, if it's isotropic and incompressible, and it is incompressible, or nearly incompressible, E should equals 3 mu. Well, in the human cornea, say about 3 megapascal is a reasonable E. Mu is about 25 kilopascal. So 3 times mu is 75, well over an order of magnitude off. No way that the cornea is isotropic. So I just answered my own question. But that makes sense. When you actually look, you know, micrographs of the cornea, it's layered sheets of collagen, okay? It's laid down in these layered sheets, and it's much more appropriately modeled as an anisotropic material. In fact, a transversely anisotropic material. We have put a sort of a variation on the theme, and what we call as a NITI, is a nearly incompressible transverse material. What that just says is that we assume that the longitudinal waves, or the traditional ultrasound waves, are isotropic. And that's not, even if they're not, that's not a big, the errors that you make are very, very small. But we do say that these shear moduli now, we have two. We have an in-plane one, and we have an out-of-plane moduli. Okay? And so G is an additional independent shear modulus. Like I said, you have one in-plane, one out-of-plane. All right? For an incompressible material, E does in fact equal 3 mu, but it's this mu which is the one corresponding to the vertical plane. And for torsional forces is determined by the G. So this description, this NITI description, captures what is the biomechanics of the cornea. So the question is can we use OCE to get at G and mu, to get at both of these? Okay, so it allows us to decouple these. Okay, so that was a good thing. And then we got the bad news. I seem to get the bad news at our weekly group meetings. I'm not sure I want to keep going back to my weekly group meetings, but anyway, we get them and said, okay, you know, when the postdocs did a you know, theoretical, did some simulations and theory calculations. Okay, consider you have a you know, a infinite half space of this NITI material, and you launch one of our waves. What do you see? Well, the speed of the wave is governed by the square root of G over rho. Okay, has nothing to do with mu. So mu, by the way, governs the Young's modulus, which is how it deforms, so therefore determines the shape, primary shape of the cornea. And we can't measure it. We're screwed. But this is where a bug becomes a feature. And I'll do this in 2 minutes and then I'll quit. Where a bug becomes a feature. Finally, because the cornea is a bounded material, this mixing of waves allows a polarization, because of the reflections, you can have polarization changes in the shear waves, which mix the waves, which mix information about mu and G. And so when you look at these dispersion relations, and we normally have two modes that we're most interested in, is they'll start to split based on the ratio between these two moduli. So let's look at one mode. I should have got rid of those slides. But anyway, let's just look at one mode so you can get the feeling. Is that when you have isotropy, that is the two moduli are the same, you have a fixed dispersion relation. But as that ratio changes, the shape and final asymptote of the dispersion relation changes. So if you have a broad enough spectrum to be able to map out precisely the dispersion relation, then you can get these two moduli independently, okay? As I just said, and can measure these fine. So that's what we've done here. We've done a quick measurement where the top, let me get the mouse up here. The top, that's an isotropic phantom we built with PVA. It gives you these interfering modes. You get the separate modes. It works just fine. We look at the cornea. We do not see that kind of interfering mode because now these modes are mixed. We see this simple mode when we fit it to this proper nitty model, we can get the two moduli. And the moduli are exactly in the range of what you get for mechanical testing, and we get their nonlinear characteristics as well. So a bug became a feature. Okay, I can see I'm out of time, so that's why I'm quitting. So what I tried to show you in a quick slapdash run through of some of this stuff is some interesting ways to think where you can bring light and sound together for generating light sound, light detecting sound, and light and sound tickling light, and hopefully some applications that could be interesting to you all. So we thank the funding people. The people in red are faculty colleagues. The people in blue are the postdocs who have worked in the group the last few years. These are ours, and one of them are Ricky, and the ones on top. I can tell you right now, the sky in Seattle does not look like that. It is full of smoke. But anyway, that's, I'll thank you and take questions. And let me stop sharing so and I'll change the camera.
Well, thank you very much, Matt. I couldn't help but think of deja vu coming up, because you started your career looking at the nature of collagen in
Yes.
myocardium.
Right, yeah.
Now you're looking at collagen in the eye.
Yeah.
40 years later.
Yeah, so it was interesting because like this air coupling thing is when the postdoc said it is, I started to laugh and everybody looked at me like, that's really not the right, you're supposed to, you were an old administrator, you should know better than doing stuff like that. But it was good. It was in, it was all in fun. And it turns out it was great. But the anisotropy stuff and the collagen, and linking to the collagen, that was, me pushing to start looking at these things. And it was based on that history from 40 something years ago. Right. And it's worked out. It's worked well.
Do you have a sense of what parameters or what kind of an image you would provide to, say, the ophthalmologist who's looking at the cornea?
Yeah, so we're just starting that. We have a great MD PhD collaborator ophthalmologist whose PhD, by the way, is in bioengineering.
Great.
And she says, at first level is that she wants to know sort of the modulus in the apex region, the central region of the cornea around it there. And then what she really wants to know is, because when she goes in to do interventions, is, okay, how's it changing? So we're trying to think about, giving more like a number as a pre-procedure thing, which can then help, a model say, okay, how's, if I make a cut here, how is it going to deform and make a cut here? But then during the procedure to try to do something differentially. So just look at and provide a delta modulus image while they're doing things. So that's the thought. We haven't done that, but I mean, that's the thought. But I always found it interesting is for their pre-surgical planning is really just a number was going to be sufficient for them, because then if you have a good biomechanical model, you can say, oh, I mean, if I take off 50 microns here or there, then the model can predict, and so they can go with that. So anyway, that's what we're thinking. Don't have a real answer yet.
Yeah, interesting. Yeah, thanks. I think Michael has a question.
Yeah,
Sure.
there are a couple of questions in the chat. One was for me, but another one from a student, I think, was how important is the line width of the optical source for obtaining good photoacoustic data?
The line width, you mean the line width in terms of optical line width, I assume, not spatial line width. But anyway, I'm assuming that the optical line width is, it doesn't have to be, we don't need high spectral purity. So typically the type of sources we use are nanometer, 2 nanometer kinds of spectral purity. So it's not that critical because we're usually looking at a few species simultaneously we're trying to separate, and their spectra are quite different. So deoxygenated blood versus oxygenated blood spectra are quite different. The contrast particles that we put in, we tune the spectra, right? So we can separate them in ways. Things like, now if you had high density quantum dots, which some people have proposed for contrast agents, then you might need some more spectral purity in the laser. But typically, nanometer, 2 nanometers is perfectly fine.
A quick question about and 1 megahertz in air.
Yeah.
The attenuation is more than 100 dB per centimeter, right? So what kind of levels do you need to end up getting?
Well, it's not 100 dB per centimeter, but it's high. But
Yeah.
it's but no, all we have to do is kick the thing so we get like a micron scale displacements. And so we've gone from like a centimeter off. So we're trying to push to 2. It's a fluid, so it goes up quadratically, right? So the losses are 4 times worse at 2 than they are at 1.
Right.
And that will probably have to be within a couple millimeters if we push up to 2. The bandwidth, because again, trying to do this spectral stuff, the bandwidth is primarily determined by the width of the mechanical source that we create, so that how tight a focus we can make. And so we want to go up in frequency. So that was the big change where stuff starting to play, is when we had sort of sloppy beams coming in to we have tightly focused few hundred micron wide beams. And I'd like to get down to about 100 micron wide as a goal. But to do that, we'll have to be within a couple millimeters of the eye.
Another question is, how did you manufacture the device that integrates laser into handheld probe in the laboratory? He's curious about the design and manufacturing process.
Okay, with great difficulty. That is a custom design. I mean, a custom device that we 3D printed onto the probe. But we're working with a big company, unnamed big company, to try to fully integrate that in a traditional ultrasound probe. And they're going to be developing the manufacturing process for that.
Okay. Okay, another question. In your photoacoustic system, you scanned the laser beam across a sample and recorded the acoustic signals. Is there a reason why you didn't just uniformly excite the laser across the surface?
That's the way you do it traditionally, but you need much more power. That's the part. So you need much more power, which is where you get these mega lasers. And by scanning it, we can bring it down because the fluence at each fiber is conserved. So if you take a fiber bundle and you come down, the fluence at each fiber is the same, but with the big lasers, they all get it simultaneously. With the little one, we get it one at a time, all right? And so the difference is because our light is only on 1 fiber at a time, our laser source goes way down, right? So you have a big laser running at low repetition rates, or a little with a lot of energy, or a little laser running at fast repetition rates, and then do this trick of scanning will give you equivalent. It's not exactly equivalent. We lose a little bit, but it's a small loss that we have by doing this, with a tremendous gain of the reduction in the size and scope of the laser.
I think there's a question, what other dynamic cellular phenomena would you be interested in trying to detect with these techniques? Okay,
so I'll answer that in terms of the spectrophotometry, because that's photoacoustic, it's optical spectroscopy in photoacoustics. So what we're looking at, the first simple thing we're looking at is trafficking of nanoparticles in cell culture. And the idea is, and what the inspiration for some of this stuff was, that in photothermal therapies and some other photodynamic therapies and others, is you do stuff and design things using spectrophotometry, you put them in the body, and they just don't work at all. And the reason is a lot of time is that the agents change, okay? And they change due to the way in which they're either bound to cells or whether the way they're endocytosed into cells. And so that's what we're looking at here is the first test is looking at change, because we can do this longitudinally. It's not real-time imaging, but by cell culture standards, it's real time. You know, it takes seconds to make the image, but that's perfectly fine, time constant for this. And so we can see how these particles are trafficked and how they change their characteristics depending on the state they're in within tissue. So that's one thing. And the second thing we're looking at, which we've done a little bit, so you know, this is pie in the sky, but I'll say it anyway because it would be cool if we can do it, is we're looking at far UV, so like 253 nanometer, that range. So where you quadruple, so you frequency double a 1064, and then you double again, right? So half of 532, whatever that is in that range of UV because we can go at nucleic acids. So the dominant absorber in cells at those wavelengths is nucleic acids. And so trying to look at subtle changes in nuclear DNA, this nucleic acids, either concentrations or changes that you would have in them, like I said, in this semi-real-time way when you're perturbing cells or doing things in cell culture. So we've gotten UV photoacoustic signals, but we've not done the experiment that I just said. And if anybody races out there to go do that, make damn sure that I'm at least acknowledged, if not a co-author.
All right, well, it's after 5, and so we need to let our speaker off the hook here. Just want to say thank you, and hopefully everyone can, react and thank you.
Well, thank you for inviting me. So
Thank you very much.
I was going to say this is that I always enjoy going to Champaign-Urbana, and this trip was one of the best ones I've had so far. So
Thank you.
For your information, he was going to get here by way of Las Vegas.
yes. And I spent Las Vegas in exactly the same place I'm spending Champaign-Urbana, and in a couple of days I'm doing the same in Pittsburgh. So it's the way it is.
Well, thank you very much. It's been very energizing talk.
Good. Okay. And for the students, if you have questions afterwards, send me notes, and I might be slow, but I will answer.
Okay. Thank you very much.
Okay.
Thank you.
See y'all.